Yeah, g'day, it's Charlie, ZL2CTM. I've just been away for a couple of days and got back and just been playing around with this little waterfall display. So I thought I'd just do a quick update day today just to look at sort of where I'm at, the current sort of thinking, and where I want to move forward with this. So what we see on the display there is a spectrum display at the top. So that's frequency along the horizontal axis and amplitude, and the waterfall diagram. This particular display here is a 320 by 240 pixel display, so I don't have a huge amount of real estate or resolution, more the point, to display frequencies, which we'll have a look at in a sec. That's currently plugged into and wired into the Teensy 3.5, and I'm just utilising the FFT analysis tool sitting within the audio library, which again we'll have a look at there. At the moment that's just listening to some music, and if we were to change that to a SIGGEN or an audio generator, then we can see there just a signal there coming through at 15 kilohertz. Let's just put the amplitude up a little bit. So maximum it's picking up at the moment through the FFT is 20 kilohertz, which is there, and then we can wind that down to essentially DC, down to 0 hertz. So that's essentially all we got to play around with, is 0 to 20 kilohertz, being an audio analysis tool. So as we mentioned in the earlier video, there's going to be that need to transpose our RF coming in down to audio to be detected here. I want to do that on the upstream side of the crystal filter, so I'm not constrained then down to that 0 to 2800 kilohertz. I want to be able to try and maximize, like I say, that 20 kilohertz available to us. So that is the desire and the thinking, and I hope we can make that work. So what I am going to do, what I've decided to do, and I'll come to that again at the end when we start thinking about the way ahead, is I've been using these quite a bit. This is the SI5351 breakout board. Typically clock 0 is the variable frequency oscillator, and clock 2 is the beat frequency oscillator. There is a spare one there, obviously clock 1 is spare, and that's the one I'm going to use to sequentially slice up sections of the RF or of the ham band, and bring those sections down to the audio range to then analyze and then to display. And at the end of this video I'll sort of talk to more about that one on how that could work. The restrictions being, each ham band is quite wide, good 200 or 300 kilohertz wide, but I've only got a screen bandwidth there of 20 kilohertz. So it's how much we want to try and display of that band on the screen, which then is a function of resolution as well. So some compromises there that need to be thought about before moving forward. For the SDR radio, obviously, I should say that, not obviously, but clock 2 and clock 0 there are those two quadrature clock signals. But again, there's still a spare one there available to dedicate to the Panadapter. Right, we'll leave it there. Okay, so in terms of putting the software together, I've mentioned before a very good online tool that Paul provides with the Teensy audio library is this thing called the Audio System Design Tool. It allows you to pull onto the screen objects that are supported by the library, which then on the right hand side tell you what that object is and how to talk to it. And then once you have objects on the screen, for example this one, it's then just a matter of physically just pulling that around and wiring these objects together to create pathways for audio, and then these objects here will produce stuff, for example, inputs, outputs, analysis, and the like. If you were to push the export button here, it would actually then give you the code for how to configure this and what to dump into the Arduino IDE. Right, so at the moment what I have hooked up for testing, and what we saw on the screen there, I've got an audio input, which is the line in. I've got wired through to a mixer, which I've notionally called input amplifier, and the output of that amplifier is going to, at the moment, to a 256 point FFT, but I also need to have a think about, and it will be more relevant at the end of this video when we talk about how to use this for a ham band. It is the 1024 point FFT. So there goes the 256 point there. It has a resolution of 172 Hertz per bin. So that's so the first 128 bins. So it's a 256. So divide that by 2 is 128. So 0 Hertz is notionally sitting in bin 0, and that 20 kilohertz is sitting around 128, or the 128th bin. So therefore giving us a resolution of 172 Hertz. Right, what's that, 128? Right, so, yeah, okay, and then the 1024 is a resolution of 43 Hertz. Right, so having now, that's the configuration of what I'm going to play around with, and that's what I've now put into the actual program itself. I won't go into this line by line, we'll just quickly race through it. I'll just sort of pick out the high points. The ILI 9341 library there, that's a specialized library that Paul's produced for this particular screen, so it's optimized for the Teensy. The audio library there, that's the one that we just saw below, the one that's been produced by Paul for the Teensy. A very good library, very powerful, you can do a whole heck of stuff with it. I've got what I'm calling a two-dimensional array here, the waterfall data. So it's 100 deep in that direction, and it's 128 wide. I'm using 128 at this point in time because I'm playing around with the 256 point FFT. So I'm just looking at those first 128 bins. So therefore the width of my array there is 128. That number, that gain there, is just notionally what I'm using to adjust that input amplifier. It's just a quick way of being able to, in software, vary the amplitude of the audio coming in before it gets analysed by the FFT. This section here, again, I'll probably do a more in-depth video in due course, but not at this point. Is just setting up the objects within the library itself, and then connecting them together. So using what they call patch cords. You can use whatever word you like, but like an old-fashioned telephone, a telephone exchange. So the input, or input left, goes to the amplifier's left input, or the output I should say of that audio input, and then the output of that audio, or that mixer, goes to the input of the FFT. Got a bit tongue-tied there, but essentially patch cords, hooking it all together. I won't go through setup. The loop itself, all it's doing there is just waiting until the FFT object that I've created, so that 256 point FFT object I've called FFT. So it's just waiting till that is available. In other words, it's done all its computations, it's done an FFT, and it's now saying to the system, hey, if you want to use the data, it's ready to go. So if that's true, I'm then running away and actually updating the display that we saw on the TFT before, or the display. The first portion is to do the spectrum, and all I'm doing there is I'm just looking at, well, first what I do is I populate the very top row of that waterfall data array. So you can see I'm populating row 0, the uppermost row, and I'm running through each of the 128 bins and populating it with the output of the FFT. So FFT output again for each of those 0 to 127 or 128 bins. Once that's been populated, I then I've just notionally called bar, so I'm just looking at the amplitude of each of those positions, and that bar is just the word I've used for that line graph, that vertical line graph. Is made up of a series of bars. The bar itself is drawn in green, and then the second part of it, so in other words the remaining portion for the height of that box that I've assigned for that spectrum, is then drawn black. The reason why I've done the second half black is the next time it goes through this, if that green bar has reduced, there's still a residual portion from the time before. So if I now overwrite that in black, we get a nice smooth display, and it always looks like it's a clean bar being drawn each time. The waterfall itself, I had been playing around with hardware scrolling, and I've also been playing around with a function within the TFT library that Paul's put up called right rect, or a right rectangle. Didn't quite do what I wanted. I wanted to have a section of the display scrolling, and I know you can do that, and I had been playing around with that, but I've sort of gone back to this sort of simplified approach. Because it's quite useful to talk about in the video. It's very easy to see and to understand, and quite frankly it works well enough for me, and I'm quite happy to stick with it. So as they say, right or wrong, that's the decision I've made. So what I'm doing here for the waterfall part is I'm running through each of the rows starting at the bottom. So I'm saying for the 100th row at the very bottom, which is 0 to 99, so I'm starting at the 99th, which is the 100th row, and I'm saying for each of the little array positions, you now equal what's just above you in the 98th. You know, run through it again and say, hey, you in the 98th row, all your data equals the 97th. And I do that all the way through, and draw it at the same time, and that gives the illusion that everything is just chunking down on the display, because it's just all that data was here. Each time through is now taken on the next position down, or the next row down, and the next row down, the next row down. So it gives that illusion that everything's moving down. And each time, as we can see up here, back at the very start of updating the display, the very top row, the very first row, has got the new data coming out of the FFT. So it's always starting at the top and flowing through down through that particular array. And that's it. That's literally all that's required to make that work. The if-else statements here, all that's doing is each time it's going through each row and each column position, it's just doing a quick test to see what the magnitude is of the data in that particular position. And depending on how large it is, depends on what color it gets assigned when it gets drawn to the display, the draw pixel. So the smallest magnitude data is assigned black, blue, yellow, and then up to yellow, blue, yellow, magenta, and then red, depending on whereabouts it sits within a couple of boundaries. I'm still playing around with those boundaries to make it look nice, but that's essentially what it's doing there. The first part of the draw pixel command, the X and the Y, looks a bit crazy here with 32 plus column times 2. All that's doing is for the test software, is just getting that waterfall to be drawn central to the main display and sitting at a certain part of the display. So that's all that's doing there. The final software, once the display's been worked out, it will be a whole lot different, but this is just to jiggery and pokey things around to make it sit where it needs to be on the screen. Right, so that now moves through, or brings us to the next part of this particular build, and that's trying to work out, and I need a bit of paper for that, how best to use this to display the spectrum of a typical ham band. Right, so the challenge we've got is trying to display a wide frequency band on a typical ham band. And that sort of, if we go 40 meter band, 7.0 through to 7.2 megahertz, on a display which is only 320 by 240 pixels. So if I've got 320 pixels here, there's really no way that I can display 200 kilohertz worth of information over 320 pixels. It's just the resolution is going to be way too low. It's not going to be good enough. So I'm going to divide that down, and I'm thinking 100 kilohertz is not too bad. So, and we'll just have a play. It may not work, but I've got to have a starting point somewhere. So if I was to sort of use 100 kilohertz, so that way, and I was to divide that into 20 kilohertz slices, then we'll be talking 5. So 5 twos are 10. So there'll be 1, 2, 3, 4, 5. So there'll be 5 20 kilohertz FFT analysis, because my FFT is technically it's 22 kilohertz wide, but I'll work on 20 to keep the numbers nice and round. So 22 kilohertz plus 22 kilohertz, or 20, 20, 20, 20, gives us 100. So that would be using that SI 5351, using that spare clock to mix our IF down into AF, and do that at 5 different frequencies to then produce these 5 little mini bands, so to speak. So that would be so using the 256 point FFT, that gives me 128 bins per analysis at 172 hertz per bin. So that's what I'll be looking at for a start. So as we can see there, so if we're talking 128 times 5, that gives us 640 elements would be needed for that waterfall data array. So that array which I'm currently storing, that multi-array there, so it's over 100, would need to have 640 elements across. Now our display is only 320, so I'd have to then only display on the display every second bin. So that would be what I'm looking to do. If that's the case, then it's going to be 172 times 2 is 344. So each, because I'm missing 172 there, missing 172. So this particular element on our display would have to represent 344 hertz. Now that's probably not so bad when it comes to, if we were look at the spectrum there, probably not so bad when it comes to an SSB signal, where I'm only looking at so 2800 hertz over 344. So that's going to roughly what's that, 8? I think it is. That would be about right, wouldn't it? Yeah. So 8 dots or 8 pixels would represent a typical SSB signal. CW is going to be a different story, being more of a discrete, and potentially I might actually miss some of those with having a resolution of only 344 hertz per dot, so, or per pixel more the point. So we'll just have to see how that one plays out when I actually go through. So that's what I'm currently thinking. If that turns out to be a resolution is not fine enough, then the next option there would be to drop our analysis down from 100 kilohertz bandwidth down to say 50 or something else. So that's also about experimenting, having a bit of a play around. So we'll see how that one plays out moving forward. So next steps now would be to make up this little circuit here. So to bring that IF down to AF. I think I'll play around with the SSB rig over there. I'll keep the SDR rig aside for now. So I'll just keep playing around with having this as a discrete setup with the Teensy on the display. So I need to add now like I say, a mixer here. So probably an AD-1. Throw in the SI5351 as a standalone device at this stage. I'll have the Teensy control that into another mixer, bring the RF from the IF down to AF, feed into there, do that over, as we just explained, over 5 separate LO frequencies to produce our 5 FFT analysis, combine those all into one big array, and then plot every second element on the display. So that's the next step. We'll see how that goes. Got a couple of business trips coming up over the next week or two, so it's going to be in and out again, but that's right. In and around that, we'll certainly get an opportunity to get into the shack and have a bit of a play around. So anyway, that was just a quick video just to sort of catch up on where we're at and where we're thinking. Like I say, I'm pretty happy with the display at the moment. If I was just to plug that back in again. Oops, I think yeah, from a fluidity point of view, that's you know, I'm quite happy with that, right or wrong. I don't think at this stage of the game I need to pursue any more the likes of hardware scrolling. And I'm kind of hoping too that I've got enough speed in the Teensy there that now that I'll be using an array which is going to be 640 points across, but you know, I can't see that slowing things down too much, so I think we'll still have a good display after that. And the other thing I can play around with at the moment, this is just every time there is an FFT analysis available, it's being displayed, so it's just going as fast as possible. It may be nice to try and smooth this out by having a running average, so maybe do over a running average over a second maybe, just to have that sort of more not so fast in reaction, but you know, a bit more sort of fluid. But that's all just tarting things up at the end. So at the moment we'll just keep how things they are, keep playing along, and go from there. I'll say 73s and keep playing at this end, and hopefully that was sort of interest. And like I say, we'll keep tinkering around. Okay, cheers all.